In section 2.3, we talk about two new rules for derivatives, the product and quotient rules. Here we have the function f of x equals x squared times e to the x and the graph of that function. So we could ask algebraically, what would we think the derivative of the function f of x should be? And you might think, oh, the derivative of x squared is 2x, and the derivative of e to the x is just e to the x. So maybe the derivative of f of x equals x squared times e to the x is this right here, 2x times e to the x. This is a reasonable assumption that maybe this could be the derivative of the red function. So let's graph this blue function and see what it looks like. Well, actually, before we graph it, let's think about what the derivative of this red graph would be. It looks like, coming up from the left, we have positive derivatives all the way up to about right here. And at -2, it looks like the derivative around here would change to 0 because the slope of that tangent line would have slope 0, and then we would turn negative for a derivative, and the derivative should be 0 again, and then positive from then on. So positive, positive, 0, negative, negative, 0, positive, positive, positive. Now we're going to graph this function here and see if that follows the rules. So this blue graph is y equals 2x times e to the x. And we can see that this graph is negative in here, but the derivative of the red should be positive right in here. Should be 0 right about here, and this blue graph is definitely not 0. So we definitely have some problems. This function here, 2x times e to the x, cannot be the derivative of f of x. So the blue graph cannot be the derivative of the red. And just from this one example, we can see that when taking the derivative of a product, you can't just take the derivative of each individual factor. It's not going to work. So now we talk about the product rule. When we want to take the derivative of a product, how is that going to work out? So if we have two functions, f and g, and they're differentiable, and then we take their product, p of x equals f of x times g of x, and we know that that's differentiable, then the derivative of that product, so p prime of x, is going to look like this. It's going to be f of x times the derivative of g of x plus the derivative of f times the function g of x. And this is the product rule. And another way that you can write this is the derivative of p of x with respect to x would be f of x times the derivative with respect to x of g of x plus the derivative with respect to x of f of x times g of x. So just using the different notation, but both of these are saying the same thing. You're going to take just kind of the regular first function in the product times the derivative of the second plus the derivative of the first part times just that regular second function in your product. And we definitely want to get a lot of practice using the product rule, so let's look at some examples. Okay, so here we have a function called f of x, and it is the product of two other functions. So this would be the first function in the product, and here is the second function in the product, and they want us to find f prime of x. So the product rule says take the first function multiplied by the derivative of the second plus the derivative of the first multiplied by the second function. So just so I'm clear, as I'm doing this, I'm going to remember this is the first and this is the second function here. Okay, so here we go. We're going to take the regular first, so that's just 1 plus x squared minus 3x to the fourth. Now times the derivative of the second. So the derivative of this second part will be 7x to the sixth minus 4 times 8 is 32x cubed. Then to that, that's only the first half, I add the derivative of the first, so the derivative of this will be, let's see, the derivative of 1 is 0, the derivative of x squared is 2x, and then the derivative of negative 3x to the fourth will be minus 12x to the third. And the last little piece is just the regular second part of the product, so just this regular. And that's x to the seventh minus 8x to the fourth. And we're actually going to leave it just like that. We could simplify all of this, multiply it out, and combine any like terms, but for right now this is good enough. We've found the derivative, and it's all of this. So again, it's not just the derivative of this times the derivative of this. The product rule says there's actually more to it. There's all of this. Okay, let's try another example. Find dy dx, or just the derivative, if y equals x squared times e to the x. And this is actually the graph on Desmos that we looked at earlier. And we know that it's not just, 2x times e to the x. We already looked graphically why that can't be true. So let's use the product rule and find the derivative of the function, the actual derivative. So dy dx should equal just the regular first part, so x squared times the derivative of the second part, the second factor, and that's e to the x, so the derivative of that is e to the x. And then to that we're going to add the derivative of the first. The derivative of x squared will be 2x. And then to that we tacked onto that is the second function, which is e to the x. So times e to the x. And this is the derivative of that graph that we were looking at earlier. So we'll look at this graphically. This is what we just found to be the derivative algebraically using the product rule. So let's graph this, and remembering that it needs to be positive, 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 and then right about here it needs to hit 0 as a y value, and then it needs to be, the derivative needs to be negative, negative, hit 0, and then be positive again. So hopefully this will follow all of those rules. And so here we have in this green graph, the graph of f prime of x, and it does follow all the rules. It's positive all through here, which it needs to be right here. The derivative of the red graph needs to be 0, and this green graph is. It needs to go negative then, and then right about here hit 0 again, and be positive after that. So it looks like the thing that we found algebraically using the product rule really is the derivative of this red original curve. Okay, let's go through another example. P of z equals z cubed times cosine of z, and we want to find the derivative p prime of z. And we'll just keep in mind that the derivative of a product will be the first times the derivative of the second plus the derivative of the first times the second. And so here's the first part of that product, and here's the second part of that product. So p prime of z should be z cubed times the derivative of cosine z, which is negative sine z, and then plus the derivative of this first one, z cubed, and that's going to be 3z squared, times just regular second function, which will be cosine z. We can clean it up a little bit by pulling this negative out front, but importantly, we've found the derivative. This is it, and so we'll just stop there for right now. Our next example is we have a function m of w, and it's 3 times w to the 17th times 4 to the w, and we want to find the derivative. We've got a lot going on here. We've got this constant multiplied out front, then this function and this function. We can think of this as two functions. We could say this is the first function and this is the second function, and remembering that this is just going to use this is just a constant multiple, and the derivative of that is, we can think of just holding this steady, pulling it out while we take the derivative of this. So importantly, we don't need to use the product rule even though this is 3 times w to the 17th. This constant multiple, we'll use the constant multiple rule for derivatives, and it just gets pulled out front while we take the derivative of this. But all of this is inside a larger product, so we still need to use the product rule for these two parts here. And so the derivative of this guy is going to be m prime of w, will be just regular first, 3w to the 17th, times the derivative of the second. So the derivative of 4 to the w will be the natural log of 4 times 4 to the w. That's the derivative of this exponential function. And now we're at this point, we'll add to that the derivative of the first, which will be 3 times 17. So let's see, 3 times 17 will be 51. W to now the 16th, and then just multiplied by regular old 4 to the w. And this is the derivative of that original function. We're looking for these 4 parts. You need to have, in a product rule, when you take the derivative, you need to really be looking for these 4 parts. Here's 1, 2, 3, 4. A couple original parts of the function, but then the derivatives of the other parts. So for this next example, we're going to find the derivative of f of x equals 1 over x times e to the x. And I'm going to have you do it, just pause the video, but here are 4 possibilities. So you pause the video and practice finding the derivative of this using the product rule and decide whether it's A, B, C, or D. So hopefully you've paused the video, and the answer to what the derivative of f of x is D. So this guy right here, let's see why that is. So we definitely have a product here, and we've got the first factor in the product and a second factor. So we'll use the product rule and say that f prime of x must equal the first times the derivative of the second, and the derivative of e to the x is e to the x. To that we'll add the derivative of the first. So this is kind of the trickiest part of it maybe. This is really just the same as x to the minus 1. So that part is x to the minus 1, and we can use the power rule for derivatives to realize that the derivative of that piece is negative x now to the negative 2, and then just regular e to the x. So this is definitely the derivative, and why would it look like this? Well, each part does have an e to the x in it, so we can factor out an e to the x out front. So that would equal e to the x, and what gets left behind is a 1 over x minus 1 over x squared. And that's exactly what this looks like. So this is the derivative of f of x. The next rule that we want to talk about is the quotient rule, and it actually comes from the product rule, but it gets its own name, and we think of this rule anytime we have a function q of x, which is really and essentially just the quotient of 2 other functions, f and g. And we'll say before we state what the rule is that we're assuming that everything is differentiable, that you could take the derivative of each of these pieces. So before I say what the derivative actually is, you should know that the derivative itself is going to end up being a quotient. And the derivative looks like this. You'll take g of x times the derivative of f of x minus f of x times the derivative of g of x. And all of this is going to be over just regular g of x squared. So one way I think of this is there's a phrase I think of low, like the low part of the quotient, d high, so the derivative of the high part, low d high minus high, the high part of the quotient, d low, the derivative of the low part over low squared. So it sounds like a weird way to remember it, but it just hopefully will eventually stick in your mind. Low d high, so low d high minus high d low, high derivative of low, over low squared. Low d high minus high d low over low squared. Yeah, so the quotient rule isn't exactly, beautiful to look at, but it has a purpose and it's super powerful, so we definitely want to know how to use it. So we'll start with this example. We have y equals x squared over e to the x plus 1, and we want to find the derivative y prime. This definitely, one of the skills that you're going to develop is being presented with a function and knowing which rule to use. We've already got several rules, and this one definitely qualifies as we'll use the quotient rule, because it is a quotient, and this is something we know how to take the derivative of. This is something we know how to take the derivative of, and this entire function is a product. Not product, quotient, sorry. This entire function is a quotient, so this is why we would want to use the quotient rule here. So we're going to start with low derivative of high minus high derivative of low all over low squared. So y prime will be low, that's e to the x plus 1, times the derivative of the high, or 2x, minus high d low. The derivative of this guy is just e to the x, because the 1 will go, when we take the derivative, will go to 0. So e to the x all over low squared, e to the x plus 1 all squared. And that's it. We'll leave it like that for now. This is the derivative. We've found it. So we'll try another example. Here we have r of z is the function 3 to the z over z to the 4th plus 1. So it looks like we have an exponential function over a polynomial function, and definitely qualifies to use the quotient rule because this whole function is the quotient of two other functions. So I encourage you to pause the video and try to find the derivative on your own using this rule, the quotient rule, and work it out and see if you get the same thing that we'll get in just a minute. All right, so hopefully you've tried this one out, finding the derivative of this using the quotient rule, but we'll go ahead and start it. R prime of z will be low d high minus high d low, so how about we try this? R prime of z will be low, the low part of the quotient, times the derivative of the high, and the derivative of 3 to the z will be natural log of 3 times 3 to the z, minus, so we're right in this part, minus high derivative of low, minus 3 to the z times the derivative of the low, and that'll be 4z cubed, the plus 1, the derivative of that is 0. Okay, so we've got the top part of our derivative, and then all of this is going to go over low squared. So z to the 4th plus 1 squared. So again, not super pretty, but you've just found the derivative of this quotient, and we could use that to do a lot of different things. Okay, we've got another example here. We're going to determine the slope of the tangent line to the curve r of x equals x squared minus 2x minus 8 over x squared minus 9 at the point where x equals 0. So slope of a tangent line definitely signals to us that we want to find the derivative. Here is our function, and it looks like a quotient. It's the quotient of two other functions, so we're going to be using quotient rule, and we have our input value of 0. So we want to find the slope of the tangent line when x equals 0. So I encourage you to pause the video and try this guy on your own. When we're finding the slope, we'll come out with an actual number, and so do all your work and come out with a number for the slope and see if you get the same number that we're about to get. Okay, so let's try this problem out together. We're going to be using the quotient rule, which is, we can remember this way also. So let's first find the derivative of r to the x, r prime of x, and it will be low d high, so x squared minus 9 times the derivative of this guy, and the derivative of that is 2x minus 2, and that's it. The derivative of this is 0. And then we have minus high, so that's going to be x squared minus 2x minus 8 times the derivative of the low, so the derivative of x squared minus 9 will be 2x. The minus 9 goes to 0, and all of this will be over x squared minus 9 squared. Okay, so we found the derivative of that quotient, that function, and now we want to find the derivative always gives the slope of the tangent line at a certain point, slope of the tangent line to the original curve, and we want to find it when x equals 0. So that's super helpful that it's x equals 0 so that a lot of things will drop out. So we want to find r prime of 0. And here we've got 0 minus 9, so that will be minus 9. And then 2 times 0 is 0, minus 2 times minus 2 minus 0 squared minus 2 times 0, so this will go away, minus 8, and then 2 times 0. Okay, so that's actually 0. So that whole part will go away. And then over 0 squared, so 0 minus 9 squared. And that'll just be minus 9 squared. And so we've got 18 minus, this will be 0. So 18 over negative 9 squared will be 81. And so this is 2/9. Okay, now we're going to look at an application of the quotient rule. When a camera flashes, the intensity I of light seen by the eye is given by this formula. I of t equals 100t over e to the t. And this is where t is in milliseconds. So t is in milliseconds. And I is in a unit called candle power. So this is how intensity is measured in this example. And what we want to do is, so what we're asked to do is compute I prime of 0.5, I prime of 2, and I prime of 5. And we're going to be asked to give the units of each of these and then interpret the meaning of each of these. So this would be a good one to pause the video and find each of these things on your own, and also take a stab at giving the units and interpreting the meaning. For this problem, we know that we're going to need to use the quotient rule to find these derivatives because we have the main function is a quotient. So to find I prime of t, we're going to do low d high, so e to the t times the derivative of high, which is the derivative of 100t, which is 100, minus high d low, and the derivative of the low is e to the t, all over low squared, so e to the t squared. So this is definitely the derivative of our function here, and we're going to plug in some values to find each of these, and we'll let our calculator do most of this work, but we're going to find I prime of 0.5, I prime of 2, and I prime of 5. So knowing that this is our derivative function here, we can just easily plug in, I use Desmos calculator to find the derivative of at each of these values, and these are the estimates, or I mean they're the values rounded off. Okay, so now we need to decide what the units of each of these numbers will be, and the units should be the output unit over the input unit. So the units should be candle power per millisecond for each of these. So 30.33 candle power per millisecond, and then at 2 milliseconds the derivative will be negative 13.53 candle power per millisecond, and then at 5 seconds the derivative will be negative 2.70 candle power per millisecond. So before we write it down, let's just try to wrap our heads around the meaning of these. So at 0.5 milliseconds,